can give some general message to our students and as well as participants.
Madam, I can't hear you.
So you give some speech for our audience and also as well as for our students, sir. Then I will introduce chief guest. Then we can start, sir.
Okay. Thank you. Very good morning to all. It is my pleasure to welcome all the participants in this webinar series, NEC Science and Humanities Talks 2020. On behalf of National Engineering College and the Department of Science and Humanities, I welcome today's guest, resource person, Dr.G.Bharath, research scientist, Khalifa University, UAE, who is going to talk on topics engineered nanomaterials for biomedical applications. Welcome you, sir. I welcome all the participants, research scholars, faculty members, my dear students and colleagues. Today is a day for celebration for us. Today is 25th Silver Jubilee webinar. In the lockdown period, for the past 2 months, we are conducting many webinars. Today is a 25th webinar, and 3,500 participants benefited from these webinars, from this lecture series. In this occasion, I want to thank all my colleagues who are constantly working for arranging the program and making the program a great success. Today's program is arranged by Dr. E. Ramachandran in order to celebrate this. In order to celebrate this 25th webinar, we planned this series. It starts from this international webinar series starts from today to Friday, 12th June, 5 continuous programs on different topics of interest with different field experts. I request all the participants to actively involve in this lecture series and interact with their resource person. I feel strongly, I believe strongly, these type of lectures will definitely benefit all of us, and it will handle to think differently. With these few words, I thank the organizers, and once again I welcome all the participants in this webinar series. Thank you all. I request Dr. E. Ramachandran to introduce our resource person. Thank you.
Thank you, sir. Good morning to all, and I'm very thankful to our management, director sir, principal sir, and our head of the department, Professor Amy Neelandan, to giving me opportunity to organize this international webinar with the continuation of our NEC Webtalk 2K20. Now I am very happy to introduce about Dr. G. Bharath, who is one of the leading and active researcher in nanoscience field. He did his PhD at Bardiyar University, and he visited many countries for research program. Now currently he is working as a research scientist at Khalifa University, UAE, and he published more than 51 international articles. I request you, Dr. G. Bharath, for giving your valuable lecture. Thank you.
So, thank you so much for all to attending this 5 days international webinar for engineering and science students. So, I would like to thank organizing committee, especially Dr. Ramachandran, and then other organizing committee people who's conducting this wonderful seminar. So, thank you so much. So, before going, we may start our session now. So today my topic is engineered nanomaterials for biomedical applications. So myself, Dr. Bharath Govindan, I'm working as a research fellow in Khalifa University, Abu Dhabi, UAE. So this is my contact mail ID. Maybe you can contact directly to me after session or whenever you have some doubts related to this topic. So today I'm going to discuss about this overall content. So nanomaterials, especially introduction for nanomaterials, because most of the people are known about nanoscience. But especially I'm discussing about the fundamentals, so introductions. Okay, so this is the first part of this content. Seminar also, and then nanotechnology in multifunctional applications, where the nanotechnology and the nanomaterials used for several applications, especially physics, chemistry, and then biological applications. So I'm going to discuss about all, and then nanotechnology in biomedical applications, how the people developed new materials, especially for biomedical applications. So I'm going to discuss about these things also, and then there is a lot of materials selections. Very important, okay, so especially for biomedical applications. So I'm going to discuss about materials, formats, why and then how we are going to select or design the particular material for biomedical applications, and then basics of nano carriers for antiviral drugs, and different drug delivery platform using nanostructures, and then carbon nanostructures. So here I'm going to discuss about two type of materials, especially for drug delivery application. One is carbon nanostructure and another one is magnetic nanoparticles, and also semiconducting nanoparticles also. So this drug delivery platform also I'm going to discuss, and then trends and target in antiviral phototherapy, and then finally the recently developed magnetic hydroxyapatite and then RGO nanocomposite, how this material useful for drug delivery application, and then how these all materials, so especially these carbon nanomaterials and then semiconducting nanomaterials, useful for recent viruses, so especially this COVID-19, how we may apply this material for COVID-19 treatment or control, and then conclusion. So these all are the overall presentation today I'm going to discussing with you all. So we know that nanotechnology, and then most of the beginners, they may know about nanoscience, the word, but they doesn't know about the basics of nanotechnology. So I'm going to discuss about the basics of nanotechnology first few slides. Then you may understand what is nanoscience and technology, and then whether it is exists in the nature or whether it is we are going to how we are preparing the materials. So many things I'm going to discuss in these slides, upcoming slides. So what is nanotechnology? The people already described about nanotechnology. It is can be defined as the design, characterization, production, and application of structures, devices, and a system by controlling shape and size at nanometer scale. The people, we already know the nanometer scale is the 10⁻⁹ meter. Okay, so nanotechnology is not new. Even the many peoples are, even the world ancient peoples also using nanomaterials. But that time we doesn't know about this is nano. The nano which is coming from after 18th or after Feynman talk only. So we know this is nano. Nano is recent words. It is like 80s words, but the people already innocent people even 1,000 years ago they used nanomaterials. So we know that the gold nanoparticles, for example, gold nanoparticles bulk material, and then gold nanoparticles in gold bulk material and then gold nanoparticles. In the gold bulk material, it shows gold in color. But when you reduce the size, so especially in the nanometer size, like 10⁻⁹ meter, it shows 10 nanometer or 5 nanometer particle size, it shows completely red color. So this is the size effect. It's the same technology that people, ancient stained glass makers, they knew when they finally ground gold or silver nanoparticles, and they would get different color, beautiful colors. Okay, so this is the thing. So even the people are prepared gold and silver nanoparticles, and then they hello. Mona? Are we clear here? Wait. நான் ஒரு கிளியரா கேக்குதா?
இப்ப கேக்குது சார், இப்ப கேக்குது.
ஓகே சார், ஓகே.
கொஞ்சம் சவுண்ட் கொஞ்சம் கூட இருந்தா நல்லா இருக்கும்.
ஓகே சார், இப்போ ஓரளவுக்கு உங்களுக்கு கேக்குது இல்ல? ஹலோ,
ஓகே சார்.
so I already explained about the nanotechnology is not new. So the golden nanoparticles, the bulk materials color in especially in the golden color. But when you reduce the size, it is effectively showing different color like red color nanoparticles. Okay, so especially 10 nanometer particle size, it shows red color, and then bulk material shows golden color. The same technology that people in stained glass makers, they used the same technology. They make it different coloring for especially for glass. So the nano particles also exist in the nature also. For example, insects and lizards are able to stick to walls because of their nanostructure on their feet. In the same time, spiders' webs are made up of super strong nanofibers, and and also butterflies' wings. Especially the butterflies' wings contain shiny reflective nanocrystals. These reflective nanocrystals also different particle size. Based on the particle size, it is emitting different color. It is based on the completely different optical properties. And then in biology, especially in the plant, the chloroplast in plant cells are so nanofactories that harness the sun energy to make the glucose. So these all are the different nanotechnologies. So especially in the nanotechnology also exists in the natures. So what are the properties of nanoparticles? How it is appearance? So especially I already explained about the gold nanoparticles in the bulk. It is shows in gold color, but when you reduce the size up to nanometer, like 10 nanometer, 5 nanometer, it is completely shows the different color, like red color, blue color. Okay, for example. So blue color, golden nanoparticles only for 50 nanometer particle size. When you reduce the fine nanoparticles like 10 nanometer or 5 nanometer, it is completely shows red color due to the surface plasma resonance. Okay, so these all are the different properties. So how the materials showing the different properties compared than bulk material. So the people said nanomaterials are superior than bulk. How it is superior? So these things very important. Okay, the people already found there is two major reason for different properties of nanomaterials compared than bulk materials. For first, the nanometer have a relatively large surface area. So when we have the large surface area, it is more, it is produced more, or it is available the surface. So especially the nanometer surface available more chemical active sites. It may be useful for the catalytic and then other biomedical applications. So we are preparing the large surface area. The nanomaterials contain large surface area. This is another one thing. And then second thing is quantum size effect. Okay, these two things are involved for the size effect. Okay, so nanomaterials. So these two things only make nanomaterials as superior than bulk material. So what are the nanoscale materials are divided into 4 categories. So first one is 0 dimension, 1 dimension, 2 dimension, and 3 dimension particles. So 0 dimension means we know that the bulk material having 3 facial direction like kx, ky, kz. It is like simply it is like length, breadth, and then height of the materials. Okay, so when we make 0 dimension nanoparticles, we just completely remove the 3 direction like length, breadth, and height. It is completely in the particle in box structures. Okay, it is completely in the quantum confinement. In the quantum confinement means we confine the electrons like the same things. Okay, we are also using in the nanotechnology. So here also the 0-dimensional nanoparticles, we completely remove the 3 direction and then it is completely into one particular point. Okay, that is called the nanodots or quantum dots. This is 0-dimensional material. And then 1-dimensional material, we have only 1 dimension, whether it is length or breadth or height. Okay, so this is one example for 1-dimensional material, like carbon nanotubes and then rods. These all are the 1-dimensional materials. And then what are the 2-dimensional materials? It has only length and breadth. For example, nanowires or nanotubes. It is a 2-dimensional material. So 1-dimensional, it is a coating surface, and then 3-dimensional material, we just that confined length, breadth, and then height of the materials. So this is the for example nanoparticles. So how the people said nanoparticles having high surface area. How it shows high surface area? If you see the cube, like 4 cubes, but in the same volume, we can use 1 cube. For example, the first figure, it shows the nanoparticles. It is just assuming for a example only, it is not nanoparticles. So for example purpose only, I'm showing about this is called nanoparticles. Okay, so when the same mass, we can put lots of nanoparticles together, but but the bulk material are only 1. Okay, so if you compare both, the same volume, we may accommodate a lot of particles, but we may accommodate only 1 bulk particles. So if the large particle, if the more particle, it provides more surface area. If it's only 1 particle, it shows less surface area. So that's why the people are, especially the people are planning to prepare nanomaterials very smaller size. When you are going to prepare the materials is very smaller size, it shows the larger surface area compared to the bulk material. For example, like it shows, for example, like this is a clear idea about the surface area, surface to volume ratio. So the first figure shows it is the 1 cube, it is 4 centimeters. The same volume, we can accommodate 8 cubes. Okay, when you reduce the size, in the same volume, if we reduce, the cube size is 1 centimeter cube, we can accommodate 64 cubes. Okay, but if you see the 3 figures, 1, 2, 3, 4 centimeter cube, 2 centimeter cube, and then 1 centimeter cube, these all are the same volume, but we can accommodate, different size of, very huge number of cubes, for example. So how to calculate surface area? So surface area is equal to base into height added up all sides. For cube, 6 sides. Okay. So here 4 centimeter cube. So base 4 centimeter and then height 4 centimeter into 6 sides. Almost we can calculate 96 centimeter square. Okay, in the first figure. But if you compare the second figure, each cubes having 2 centimeter base, 2 centimeter height, and then 6 sides, but here we can accommodate 8 cubes. Okay, so therefore 24 centimeter square into 8 cubes, 192 centimeter square. If you see 4 centimeter cube particle shows only 96 centimeter square surface area, but a 2 centimeter cube particle shows, that cube shows 192 centimeter square. In the same, you can see 1 centimeter cube, it also shows 384 centimeter square. It is just example. So when you reduce the size, you can accommodate more particles. If you accommodate more particles, it is provide a large surface area. So this is the basic principle of why we are designing the nanomaterial for multifunctional applications. So the next, actually, I already told there is a 2 key factor to decide the material properties, especially nanomaterial properties. One is surface area and another one is quantum confinement. Okay, so now we are going to discuss about the quantum confinement. So in nanocrystal, the electronic energy levels are not continuous as in the bulk, but are the discrete because of the confined of the electron wave function to the physical dimension. So if you see the bulk material, we know that in the bulk material having lot of atoms. Okay, in the all atoms creating different electronic energy, these different electronic energy overlap each other, okay, and then produce the continuous energy level when we just seeing about the especially when we are seeing about the bulk material. But if you compare the nanomaterials, we reduce the particles, okay, so size of the materials. When you reduce the size of the materials, it is also reduce the particle size and then atomic level also, okay. Then you can reduce the electronic energy levels, okay. It is not continuous energy levels when you comparing bulk material. It is a discrete energy level, the same like the single atoms. The single atoms having the discrete energy level, but in the bulk material having the continuous energy level. So this is completely full and full the quantum mechanics, okay. So if you see, just for example, in the first figure, you can see the bulk semiconductor. We know that the semiconductor, the material classified conductor, semiconductor, and then insulator. Conductor means the conduction band and the valence band are overlapped each other, and then electrons are freely move to the throughout the material, okay, throughout the lattice or throughout the material. That is called the conductor. In the semiconductor, we have the small energy gap between the valence band and the conduction band. When the light energy or some external energy is stimulated to the passed to the valence band, the valence band electrons are take that energy, and then it goes to the conduction band, okay. So this is so in the conduction band, electrons are reason for conductivity of the material, okay. So this is called a semiconductor. But in the insulator, there is a large gap between conduction band and valence band. So it is not easy to stimulate the electrons from valence band to conduction band. So normally we classify three conductor and another one level superconductor. Okay, so conductor, semiconductor, and the insulator. The most of the people, the electronic line, especially electronic devices, and then most of the material, solar cell, and then most of the applications, the peoples are using different type of semiconducting nanomaterials. So I'm going to explain about the semiconducting nanostructure. So if you see that second figure in the second figure in the bottom, okay, bottom figure, in the bulk semiconductor, it shows some energy gap. When you reduce the size, the gap increased. Why the gap increased? Energy gap increased because of the energy levels decreased. Okay, in the bulk semiconductor, a lot of energy levels are overlapped each other, and then it is completely continuous energy structure. But if you see the the quantum dots, because we are reducing the size as well as we are reducing the energy levels also, okay. So if you reduce the size, increasing the energy level, increasing the energy gap due to the decreasing the energy levels or overlapping the energy levels, okay. So that's the only reason bulk semiconductor shows different properties, and then big quantum dot shows different properties, and then small quantum dot shows different properties. The properties may be optical, magnetic, or any other material. Okay, so this is the main reason why we are selecting nanomaterials for multifunctional applications. Okay, so for example, so quantum dot. So the people are using semiconducting quantum dots for solar cell applications. Okay, and then as well as they are using imaging purpose also, cell imaging purpose. There's so many applications there. So many applications they are designing for quantum dots. So 3 quantum dots size like 50 nanometers. So you can accommodate almost in the 2 centimeter length. You can accommodate almost 40 million thousand dots. Okay, this is the main advantages. Okay, so if we reduce the particle size, we can accommodate a large n number of particles in the particular volume. So that's the only reason we are dealing about the quantum dots. So how it is shows the different color, I already told. The different color is mainly due to the band gap of the materials. When we tune the band gap of the material, like when we tune the band gap, it is maybe related to the size of the material. Okay, if for simple, if you reduce the size, increasing the band gap. If it is increasing the band gap, it shows different color effect. So this is the simple concept. Okay, so the people are designing various semiconducting nanomaterials, especially for biomedical applications or optical applications. Okay, so this is the basic principles. So nanomaterials, basically nanomaterials showing different properties due to the more surface area and then quantum confinement effect. So these things are very important when we designing the nanomaterials. So based on your application, we may design 10 nanometer particles or 5 nanometer particles for your applications. Okay, so there is two different approaches to synthesize or fabricate nanomaterials. So especially top-down approach and bottom-up approach. In the top-down approach, we have already bulk material. From the bulk material, we just cut away the various material or reduce the particle size to make nano size. So this is called top-down approach. And then bottom-up approach. So we know that such atoms and molecules, from the atoms and molecules, we build to the nanoscale. Okay, this is the bottom-up approach. So top-down means bulk to nano, and then top-down means bulk to nano, bottom-up means molecules are atom to nano. So these both are two different approaches for nanomaterial synthesis. Okay. So these all are the different example for top-down approach, lithography milling. This is for example, and then another one method, bottom-up approaches. So here we can see that two different methods for gas-phase and then wet chemical. In gas-phase, physical vapor PVD deposition, and then chemical CVD deposition, laser ablation, molecular beam spraying, aerosol. These all are based on the gas phase. And then wet chemical like microemulsion, thermal decomposition, hydrothermal, solvothermal, sol-gel method, photochemical, sonochemical, chemical reduction, electrochemical. These all belongs to the wet chemical techniques. So once we prepare the material, we should characterize the material, like whether we prepare the same material or other material, or we prepared with a pure material or with any other impurities. Okay, so we should find this information from several analytical tools, especially structural, optical, electrical, and magnetic properties. We should properties. So in the structural analysis, so especially marbology for scanning electron microscope, atomic force microscope, and then scanning tunneling microscope used for to identify the marbology of the materials, and then crystal structure like X-ray diffracts analysis, synchrotron, and then TEM, transmission electron microscope. So we can find these things, transmission, especially SAD pattern. From these analytical techniques, we identify the crystal structure of the material. And then composition, especially EDS and then XPS, we may identify the composition of the material. So these all are the structural analysis. And then optical analysis. Suppose your material is semiconducting material, you are going to use your material especially for optical applications. So you may use these techniques, especially photoluminescence, Fourier transform, FTIR, and then scanning near optical mirror and the Raman spectroscopy to identify your materials, optical properties of your materials. So UV also belongs to these optical properties. And then electrical properties. So if you want to find your material electrical property, so carrier concentration, contact resistance, mobility, and then these all are the different electrical measurement. And then magnetic property, especially VSM squared, and then magnetic force microscopy. These all are the different techniques to identify the magnetic properties of the material. So, so especially I'm going to discuss about the nanomaterials for biological application. So nanoscience is not a single field, it is combined with physics, chemistry, and then biology. We know that the metal particles preparations and then polymeric nanoparticle development, carbon-based material, these all are the chemical field, but we may use some physical equipment to characterize this material. Okay, and then once you characterize this material, we successfully used this material for biomedicine, biotechnology, and then biology applications. Okay, so nanotechnology is not a single field, it is combined field with chemistry, physics, biology, and then engineering. Okay, so these all are the common platform for nanotechnology. So especially how the material select the material for biomedical application. So here actually the research people always think about four important factor to design this material for biological application. For example, material designing. The people are, the people are designing several nanomaterials like metal particles, carbon nanotube, dendrimer, protein drug conjugate, liposome, solid lipid hybrid particles, hydrogel particles, and then polymeric particles. Okay, so the people are developing different nanoparticles for biomedical application. So each material showing different property, and then each material having different, different biomedical properties. Therefore, the people are designing according to their need, and then the people selected, and then people designing different shape of the particles. So especially rod, star, cube, plate, and then sphere. Why the people are concerning the shape of the particles? For example, gold nanoparticles. Gold sphere nanoparticles having different property, rod nanoparticles having different property. For example, rod nanoparticles, mostly the gold nano rod particles useful for cancer treatment. So because when you pass the light to the gold nanoparticles rod, it is produce internal heat like 42, 43 degrees centigrade, and then this temperature is enough to kill the cancer cell. Therefore, the people are used gold rod nanoparticles for biomedical application. So the people are designing, especially the research people are designing the different shape what they want. Okay, so these all are the basics of research platform, and then surface also. So how we modify the surface of the nanomaterials, the speculation or other coating, functionalization of the material like minus SH, and then amine and then carboxylic group used for the functionalization of the material, and then surface charge. We can tune the surface charge of the material also, and then targeting ligand. Maybe some ligand we may attach like antibody peptide and then aptamer. We can use these materials, and then finally size of the material. So especially the 100 nanometer to 1 nanometer particle size, the people have used several applications, especially biomedical application. Like 2 nanometer particle size is very easy to penetrate the inside cell or inside the nucleus compared than 100 nanometer particle size. So based on the application, what type of application we're going to use, so you may design your materials like say size of the material, shape of the material, surface charge of the material, and then what type of material you have to prepare. So these are the material formats that mostly the people are, research people are designing or engineering their material based on these four key factors. And then, for example, nano carriers for antiviral drugs, the people have developed so many nano carriers for antiviral drugs. So, for example, metal nanoparticles, polymeric nanoparticles, nanostructured lipid carriers, solid lipid nanoparticles, micelle, and then liposome emulsion, and then surface dendrimer, and then nanogel. So these all are the different nano carrier. These all are the nano carriers. It is carry the antiviral drugs to deliver the cancer cell treatment or any any virus. Okay, for example, metal nanoparticles. So you can load your your antiviral drugs onto the metal nanoparticles. Metal nanoparticles. Metal nanoparticles. Okay, so you can load your antiviral metal nanoparticles to the by using various techniques, and then you can control deliver to the particular virus. Okay, this metal nanoparticles also useful for as nano carrier for antiviral drug release and loading and release also. And then polymeric nanoparticles. Some polymeric nanoparticles are very biocompatible, and when you are designing this type of material, it is very easy to carry the antiviral drugs into the virus. Okay. Hello. Yeah. Parana?
குறித்து அதன் பற்களை உடைத்தும் தெருவில் தாசனவன இழுத்துச் சென்றும் சித்திரவதை
Now, okay. So I'm sorry for the technical interpretations. Okay, so some technical interrupt always having through this webinar seminar. So I'm sorry about that. So these all are the different nano carriers for antiviral drugs. For example, metal nanoparticles, polymeric nanoparticles, nanostructured lipid carriers, solid lipid nanoparticles, and then liposome emulsion, and then nanogel. The antiviral drugs are loaded to the metal nanoparticles or polymeric nanoparticles or nanostructured lipid carrier or solid lipid nanoparticles. So we may load the antiviral drug. What type of antiviral drug we have to load? First you design your material, and then you have to load your antiviral drug to that material, and then you can easily penetrate this material to your what type of target you want to deliver. Okay, so targeted delivery, the target may be virus or any cancer cells or any other species. Okay, so these all are the different types of material we may design this one of the material for any other particular applications. So especially antiviral drugs also we can load, and then we can release this material, we can release these antiviral drugs to virus, so particular virus. So for this application, especially the people are used carbon materials for biomedical applications, because carbon nanotubes, so especially carbon nanotubes, and then C60 graphene, and then graphene oxide, and the nano diamonds. So these all are the different allotropes of the carbon. These may useful for drug delivery applications, cellular therapy, photodynamic, photothermal, Raman imaging, optical imaging, cellular imaging. So we may use several carbon allotropes for various applications, especially biomedical applications. For example, the people recently developed advanced functional carbon nanotubes for antiviral drugs, loading and then releasing. So for this application, we have to functionalize this material by using polymer, and then targeting moiety also. We have to functionalize the targeting moiety, and then therapeutic molecules. So what type of therapeutic molecules you have to release the particular targeting molecules. So you have to load the particular therapeutic molecules to the carbon nanotubes, and then nucleic acids. So what type of nucleic acid you have to load, you have to attach with that your materials, and then diagnostic agent. So diagnostic agent is very easy to so especially this diagnostic agent is very easy to monitor the where your materials is going, so especially inside the cells. So we can easily monitor outside, okay, when we just using the microscope images, especially cellular images. So these all are the different advanced functional carbon nanotubes material for using biomedical applications. So in this work, the people are loaded the therapeutic molecules. Then there is a two type of active and then passive penetration. From the passive, through the passive penetration, it is a lipid bilayer penetration. It is already penetrated to the inside cell, and then once it reach to the inside cell, and then we may use the external trigger, maybe external trigger like light energy or any magnetic field. If suppose the people are used magnetic material, they may use the magnetic field. Magnetic material, magnetic field, or any light sensitive material like any semiconducting material or other material, we may use external trigger as light energy or photon energy or laser energy. So these all are the external trigger. When we use the external trigger, uh, uh, use the external trigger, we may release the drugs to the complete the cell. Okay, this is the final the complete the drug delivery platform when we are using advanced functionalized carbon nanomaterials for these particular applications. So the same techniques we may use for viral especially viral therapeutic agents also. Okay, so these are the basic principles, and the people are developed the same way the people are developed hydroxyapatite and then graphene nanocomposite for biomedical applications. So especially the prepared Okay. Okay, va. Hello. Okay. So this is the, for example, how the carbon nanomaterials useful for carbon nanomaterials useful for antiviral drug releasing. So, for example, when we are developing the carbon nanomaterials, because it is a raw material, it is not easily, really, it is not easily dispersed in the water or any other solvents. So, for this reason, we always, attach any polymer like PEG and then other polymers to functionalize this material. And other things, the targeting moiety. So we need some particular receptor, especially peptide, to this is called a targeting moiety. Without this targeting moiety, the materials is not connected to the inside cells. It may be the protein pilase or peptides or something. And then therapeutic molecules. So we may load the therapeutic molecules. What type of molecules you have to load? For example, the people are developing various antivirus drugs to deliver the particular virus. Okay, so for this reason, they just load their therapeutic molecules to the functionalized carbon nanomaterials, and at the same time they attach a nucleic acid and then diagnostic agent. So these all are the different diagnostic agent to functionalize this material. And then when you loaded your therapeutic agent, and then after you just inject this material to your body or cell lines, then it is easily penetrate to the inside. So once it is penetrate to the inside, you have to apply any external triggers, like suppose magnetic materials, you may apply some magnetic field to deliver therapeutic molecules. And at the same time, if maybe these materials are photoactive material, we may use this material, we may use some external energy, like sunlight or laser or any near infrared wavelength, that type of light you may use to deliver your therapeutic molecules. So when you use this type of external trigger, it is completely release your therapeutic molecules, and then after especially the lysosome, it is destroy the completely carbon nanomaterials. Okay, so these people. So especially recently, the researcher developed advanced functionalized carbon nanomaterials for antiviral drug loading and then releasing. So these all are the basic principles how they are proposing their mechanism for antiviral drugs molecules to deliver to the particular virus. So these all are the very important. So recently, the people are developed a graphene and a biocomposite material. So especially graphene and then hydroxyapatite nanomaterials for application. So especially that there is one application. So the most by skin cancer, maybe it is UV radiation or some other external reason they affect skin cancer. Okay, so the people developed androcrafide. This is anti-cancer drug for skin cancer. Okay, they loaded and that androcrafide drugs to the hydroxyapatite and then graphene nanocomposite, and then it is easily deliver this material to the cancer cell lines within 24 hours. So we almost half of the cancer cell killed within 24 hours. So the people have developed the hydroxyapatite as a vehicle to carry the androcrafide to the cancer cell lines. So these are the one engineering material. These may be useful for biomedical engineering applications. So another one is the magnetic nanoparticles in biomedical applications. So especially the magnetic nanoparticles used in several fields like photothermal therapy, gene delivery, drug delivery, contrast agent, and then cell imaging, and then anti-cancer agent, cancer diagnostic and then treatment of bacterial and viral infection. So that people are used in several applications by using these magnetic nanoparticles. These magnetic nanoparticles may be in diapara, ferro, and the antiferromagnetic materials. The people mostly use the superparamagnetic for multifunctional, especially biomedical applications. Why the people are using the superparamagnetic material? Because it shows very low, actually negligible coercivity, and then it shows higher magnetic properties. When you use this magnetic material for biomedical application, it is very easy to control your material by just applying external magnetic field. Okay. So this is the main reason. Recently, the people are focusing magnetic nanoparticles as biomedical for biomedical application. For example, the magnetic nanoparticles. We know that antibody targeting ability. So antibody, we may design these nanoparticles, magnetic nanoparticles useful for biomedical application. So for antibody, we may just attach the antibody and then peptides. This peptide is facilitating to cell entry. And then polyethylene glycol, it is giving the dispersion ability of the particular nanoparticles, and maybe it is giving the biocompatibility of the nanoparticles. And then antiviral nucleic acid, maybe it is whether it is antiviral nucleic acid for antiviral therapeutics or any antiviral drugs, maybe any other drugs, we may load the particular drugs to the material surface. And then these materials are, this is the complete nanocarrier platform. When you use this material, we can directly control by external magnetic field, and then it is directly to deliver to the particular cell lines. So the cell lines may be cancer cell or any other virus. So this is one type of application. How the people are using this type of applications. And then recent trends, the people are, because you know that now this pandemic situation, so especially Corona, the people said even the coronavirus living 12 hours, even 18 hours in the other side, even in the metal also, on the metal also it lives almost 8 to 6 hours, even 8 to 6 hours, even 12 hours also. So for this application, how we control this type of virus in outside. So this is another one major task that people are currently working this type of work. Okay. So for example, they developed semiconducting nanomaterial or any type of photosensitive nanomaterial. They developed this material and then they coated on the surface, metal surface, and then they just just put some virus on the surface, and then after just applying some light, this light kill the virus. So especially the virus. Why it is killing the virus? Because the photosensitizer, especially semiconducting nanoparticles, it is react with light and also atmospheric oxygen. It is produce reactive oxygen species. These reactive oxygen species are reason to kill the virus. So especially outside the virus. For example, the people are developed recently. The people are developed iron oxide nanoparticles, and then iron oxide, especially Fe2O3 nanoparticle. Fe2O3 nanoparticles is one of the semiconducting nanomaterials. It is also having 2.2 electron volt band gap. It is also sensitive material. So these particular materials, when they composite with the graphene and then Fe2O3 materials, and then they just pass the sunlight, it is produced the ROS. This ROS means reactive oxygen species. So this reactive oxygen species is kill the cancers immediately. So the virus immediately when the metal surface, we just coat the metal surfaces. This is also another one application. And then how it is kill the cancer cell? Because when the nanostructured semiconductor, it is produced, it is particles. Okay, it is when the light interact with the semiconducting nanomaterial, it is produced valence band, and it having valence band and then conduction band. So the valence band, when the light strike on the valence band, it is produce excited electrons. These excited electrons are excited to the conduction band, and then conduction band electrons are react with environmental oxygen, and it is produced OX, actually O oxygen radicals. These oxygen radicals only kill the virus. Okay, so if we just coat any titanium oxide nanoparticle, this is also example for titanium oxide nanoparticles. If you just kill the if you just coat your material, especially in the substrate, okay, the substrate should be maybe in the bus handle or anywhere that people are commonly used the particular in the common platform that people are using in the common platform, you may just coat on your titanium oxide or any Fe2O3 nanoparticles on the surface. It may just produce the oxygen radicals. These oxygen radicals is easy or immediately kill the viruses within 5 to 10 minutes. Okay, so these all are the advanced applications. The people are focusing this type of material for virus control. So especially COVID control also it is possible to control. Okay. So another things that people are produced the magnetic hydroxyapatite nanoparticles. These magnetic hydroxyapatite nanoparticles are very useful for drug delivery applications. So especially they used they used hemoglobin separation. So why the hemoglobin separated among the BSC and the lactase? It is full and full based on the pH. So pH of the material. So pH of the material is maybe related to the surface charge of the materials. If you change the surface charge, if you change the pH, it is ultimately change the surface area as well as surface charge. This surface charge is easily attract to the electrostatic attraction between hemoglobin and then your material, and then easily collect or separate to the material. So this is also another one particular applications where the people are used nowadays these type of materials for drug delivery applications also. Okay, so so they compared other materials. So these materials shows the higher drug loading and then higher releasing. So for example, so when we load the hemoglobin, it is just 30 minutes, it's completely loaded your material, almost 1200 milligram you can load within milligram per gram. We can load even 50 gram of your materials. So this is that maximum surface area. That's why we are focusing on nanomaterials. If you just use the nanomaterials, provide more surface area, and then it is provide more active at certain site for absorbing drugs or hemoglobins or any other content. So in the cumulative release also, so within 30 minutes or 40 minutes, it's completely released the drugs, and then in the pH 4. So maybe this design completely useful for cancer cell treatment. So people are developing this type of material for cancer cell treatment. So these all are the different example for multifunctional application. Like these materials is potentially useful for maximum drug absorption, and then it is completely released within 45 minutes. Especially 85% of drugs, it is completely released, and then it is magnetic material, so we can easily handle with external magnetic field. This is also another one applications, and also these materials may be useful for antiviral drug delivery platform for COVID-19. So these all are the different example for multifunctional applications. So thank you so much for so thank you so much for attending this seminar.
Okay, Bharat. Now, audience or participants are asked if you have any question, raise your question, or post your question in chat box. Question யாருன்னா? No more question. Question யாரோ கேட்டிருந்தாங்க. Dear participant, if you have any question, you can clarify with our resource person.
Yeah, you may contact through my email
Okay.
also. If you have any questions related to this topic, you may contact.
Okay, you can, dear participant, you can note your resource person mail ID. If you have any clarification, you can write email to him. Because thank you, Dr. Bharat, for
Thank you
accepting
very
our
much.
invitation at your busy schedule. I know you are going to give another session to another college. So thank you very much, Bharat. So in future, we will conduct for
Yeah,
another
yeah. Thank you. Thank you so
series.
much.
Okay, thank you, participants. So now we are going to post feedback form. Kindly fill the form. Kindly submit the feedback form. Okay, Bharat.
ராமச்சந்திரன் சார் நம்மளும் ஃபில் பண்ணணுமா?
Okay.